So again, so for today, we're on to chapter 5 and functions. So yeah, first off, in ternary relation, which is a set of ordered pairs. So I have an example there. 1, 2, 3, 4, 5, 6, 5, 7, 8, 10. Right? So it's a set of ordered pairs. Right? Right? So the next step up from a relation then is if you have what is called a function. And so for a function, you have for every x only one y. So you have in turn 1, 2, 5, 7, 12, so that would be a function. For every x, there is only one y value. Right? Every x goes on. So given a set of points, can you tell if it's a function or not? Okay. And another thing then is given an equation. Is it a function or not? So for example, if I have this, is that a function?
Yes.
Right. We got 1 yeses and 2 nos. What do you think, Tyree?
It's a quadratic.
What?
It's a function.
What do you say?
It's function.
Alright. So this side says yes, this side says no, and in this case, this side is correct. Right? Right? Alright. So yeah, so whatever number I plug in for x, right? If I plug in ax number, I only get one y number out, right? So therefore it is a function, right? Every x number I plug in, I will only get one answer, right? So that makes it a function, right? So for example, I say, okay, so solve this if x is equal to 5. So if x is 5, what do we get? X is 5, the answer is
128.
no, you are right.
Oh, okay.
Yeah. So if x is 5, then y will indeed be 128, right? So then you get in turn what is called function notation. And so I can rewrite this same equation saying f of x is equal to 4x squared plus 5x plus 3. Right? And now I can ask that same question and say, okay, well, what is the f of 5? And you would get the same answer as what we just did, and that would be that the answer to that is going to be 128. Basically what this says is everywhere you see the x, plug in that number and evaluate. Is that a function?
Yes.
No. That's stupid enough.
You're going to say we no. You're just on the contrary side of the world over there today, right? Okay. Yes or no?
No.
Well, in this case, that side of the world is correct.
Really?
Really? Because What is the square root of 25? And?
Negative 5.
Right.
Oh, here we go.
Right? Yeah, so yes. The square root of 25 is actually both positive 5 and negative 5, right? Even though if you ask somebody down the street what the square root of 25 is, they'll just tell you the one answer, which is going to be 5. Provided they actually know what the square root is when you ask them that question, right? Yeah. But yeah, that would not be a function because this would give you about 2 answers. And so that one number, that one x number, is going to 2 different y values, right? Right? Let's see other functions, integer function. So let's say we have this function, our integer function, that we have, and it's going to be defined that f of x is equal to x squared. And so that means we would have the following set of numbers. Negative 39, negative 4, negative 1, 0, 0, 1, 1, the dot, and so on, right? And then we could also write out the same thing using what was in set builder notation. And so f is going to equal the set of xy. So I said xy is an element of the integers, and then y is equal to x. So rather the same thing, but now we're out in terms of that set builder notation, right? Let's see, everybody remembers the terms domain and range? Yes, no, maybe? Domain and range? So given something like this, and I ask what is the domain? Okay. Again, the domain refers to the x values. And so my domain here would be the numbers 1, 3, 5, and 7. And then if I want to know what is the range then refers to the y values, which in this case would be the numbers 2, 4, 6, and 8. Right? Right? So the domain was the x, the range was y. Right? Now, except for in the case of this book, and they use a different term. The domain is still the domain, so what you're used to as far as what that means. But in the book, instead of using the word range, they call this the image. Bailey again is range. Okay? So you got domain, you got range. So given some examples like this, so what is the domain? And we'll use their I have this? We had this one up on the board earlier. So domain, what numbers can I plug in for x?
Infinity.
All numbers, right? All reals? So my domain is all real numbers, right? Right. What is the image? So once I plug in all those numbers, what kind of numbers come out? So can I get negative numbers? Yeah, I can get negative numbers. Can I get 0? There'll be some weird number where you scan. And I can get any number I want out of this, right? So my image is going to be all right? Right? How about this one? F of x equals what numbers can I plug in for x? All real numbers, right? So my x values, I can plug in whatever I want. So my domain is all reals. And what do I get out of that once I plug in all those numbers?
Real numbers that are positive.
Real numbers that are positive. How about 0? Shrink it. Because after all, if x is -4, -4 plus 4 is 0. The absolute value of 0 is 0. 5 times 0 is 0, right? And so my image is going to be numbers that are greater than or equal to 0, right? Right? Now this one we are talking about, you notice that I have this one down as being f of x equals the square root of something. So this one we're actually talking about the square root function, okay? Not like the one I had earlier where I just said square root. So in the square root function, it's basically doing like most people would say, if I ask somebody what the square root of 25 is, they would only tell you the one answer, which is 5, okay? So we're only looking at the positive answer. So, given this one, what is the domain? No, it's not. Not all reals this time.
It's anything greater than -5, right?
Anything what?
Anything greater than -5.
Anything greater than? So x has to be greater than or equal to 5, right? That's why I cannot take square root. In the real number system, we cannot do square roots of negative numbers, right? But I can do the square root of 0, because the square root of 0 is 0, right? And given that we're talking about the square root function, okay, what answers come out?
Positive numbers.
Right. So again, it'll be numbers. So this will be numbers that are greater than or equal to 0. And again, we're just looking at the top half of that curve, right? Right. And let's do one more. Given that one, what is the domain? What?
All reals.
No, not all reals. So, what numbers can I plug in for x? Or better yet, what number can I not plug in for x?
Negative 3, right?
Yeah. There's one number that I cannot plug in. Only one number, okay? And so here the domain is x cannot be negative 3, right? So if you have x in the denominator, you got to ask, do you feel lucky? Right? But you got to ask, is there a value of x where the bottom term would be 0? Because after all, you cannot divide by 0, right? And so, yeah. And so I can plug any number but negative 3, right? Right? Right. Right. When I do that, what kind of numbers come up? Can I get negative numbers?
Yeah.
Can I get 0?
Yeah.
Can I get positive numbers?
Yeah.
Right. Sounds like all reals, right? All right. Right. So you have given an equation, given a set of points, can you tell it's a function or not? Given, can you tell with the domain or the images of a function? And the other thing then, in terms of a graph, so to think back to when you were younger, before all this stuff, right? And back to children's TV, and that longtime staple being Sesame Street, right? And you got to that one segment in Sesame Street that said one of these is not like the others. And that is true in terms of my pictures that I have up here on the board, because one of these is indeed not like the others. One of those is actually a picture of a function, and the other ones are not. So is A a function? Is B a function? Is C a function? Is D a function? If you said yes more than one time, we got it wrong, right? But that's the way you tell in terms of if a function I got, in terms of the vertical line test. So if I take this, you notice it cuts that red line in 3 spots, therefore it's not a function. Here, I cut it in a couple spots, not a function. Here, everywhere it is only one time. That is a function. And then of course over here, a couple times, it's not a function, right? So C is a function. Right? Everywhere, it only cuts that red line in one spot. So for every x, there's only one y. After all, you think back again to when you were a kid, I saw the news that the Schoolhouse Rock guy died.
I was like 9.
You weren't, I know. You guys are too young for that one, huh? I am a Bill, conjunction. Oh, good old. Oh, gosh. You're too young. Right. 1, 2, 3. So I got 2 sets, A and B. A has the elements 1, 2, 3. B has the elements 4, 5. And we want to find all functions A. And so the number of functions, so the number of ways this can be done. From A to B. Going to be given by, so I need to know the cardinality of A, which is given by A, and then the cardinality of B, which we'll say is given by B. And so this will be given by B to the A power. Right? So what is the cardinality of my set A? 3. And the cardinality of B is 2, right? Again, cardinality is how many elements are there, right?
Yeah.
Right? And so the number of ways this can be done then, and so we said the cardinality of A is equal to 3, the cardinality of B is equal to 2, and so this is going to be 2 to the 3rd power, which is
6, 8.
I did 3 to the same.
okay. All right. All right, we got all kinds of variations on that one. All right. Okay. And then we can look and determine, well, what are all of those possibilities, right? So after all, we said this can be done 8 ways in terms of this, right? And so we can have 1, 4, 2, 4, 3, 4, 1, 4, 2, 4, 5, 2, 5, 5, 3, 4, 1, 4, 2, 5, 3, 5. And then we have 1, 5, 2, 4, 3, 4, 1, 5, 2, 4, 3, 5, 1, 5, 2, 5, 3, 4, and then lastly 1, 5, 2, 5, and 3, 5. Right? So that would be all the different ways that could be done. Right? So we know there's 8 possibilities, and then it's a matter of going through and actually coming up with all 8 possibilities. And sort of being systematic when you try to do this. Okay? Alright? Alright. So it's got in terms of function. We can also look in terms of the inverse of the function. Wait a moment here. I'll actually write this down. You guys are too young for Schoolhouse Rock, huh? Watching Elementary.
Yeah, they still replay it in high school and stuff. I have no idea what it is.
No way.
I mean, I'm also from Mexico, so
Oh, okay, all right. Okay.
we might not have it down there.
Oh, okay, all right. Okay,
Maybe.
all right.
Email.
So inverse of a function. So if f is given by set of 1, 2, 3, 4, 5, inverse of f would then just be the set 1, 4, 3, 6, 5, 8, 7, 8. So the inverse, all you gotta do is just flip flop the x and the y, right? So yet in terms of relation, which is a set of ordered pairs, we had functions which said for every x there is only one y, right? And then we can move a step up from that, and we could go to whether or not the function is then 1-to-1. And so you get to having a 1-to-1 function. And so now we have for every x only one y, and for every y only one. So for every x there's only one y, and for every y there is only one x. So the way you can tell this by looking at a graph, we'll do the easy example first. That's the easy example. Right? That is 1-to-1. Right? And the way you can tell in terms of looking at a graph, so before we said to tell, remember my picture of the 4 graphs? We said the way you could tell was a function was that when you did this, it crossed everywhere one point, right? Now the way you can also tell if it's 1-to-1 is it has to pass this test, but it also has to pass this test, right? So it's got to pass both the vertical and the horizontal line test, right? For it to be 1-to-1. Exponential graph, right? Y equals 10 to the x, right? After all, it never will be 0, right? Because remember the real rule about exponents, negative exponent means 1 over that thing is a positive exponent, right? And 1 divided by whatever number, no matter how big it is, will never actually be 0, right? Right? So that's your exponential graph, okay? Okay, remember back from the little days of your algebra trig stuff, you had exponential graphs, then you also had logarithmic graphs, right? And the logarithmic graph then was the one that went like this. Right? Logarithms, right? Well, if I look at this black one, again, remember domain is the x value, right? So this graph tells me if I look at it, the x numbers that I can plug in here are going to be all real numbers. And then the y numbers, or the image I get out, are going to be numbers that are greater than 0. Okay? So I get numbers that are greater than 0. Right? Now, if I look at my red graph, my log graph, well now, the numbers that I can plug in are numbers that are greater than 0, and the numbers I get out are all real numbers. Right? So 10 to the x and log are inverses of each other. Right? The domain of the one becomes the range or the inverse of the other. And so this graph, if I look at just my exponential graph, it is 1 to 1. If I look in terms of my log graph, which is the red one, it is 1 to 1. Okay? And so you have that if they truly are 1 to 1, that the domain of that is going to be the image of the inverse, okay? And then the image of f is going to be the domain of the inverse, okay? Just like we just wrote up there on the board on my graph, right? That if they are 1 to 1, then the domain of the one becomes the image of the other. The domain and range. Everything back in terms of numerical terms. Okay. Question on that? Okay. Well, so we got the function and its inverse. Forward and line, right? So there's my function, all right? And if it's easier to look at this, because after all, f of x is basically the same thing as saying y. So let's say this is y equals 3x plus 4, right? I want to write the inverse. Well, to write the inverse, all you have to do is flip-flop x and y. And so now this becomes x is going to equal 3y plus 4, right? All you do is flip-flop x's and y's, right? And so, again, this was my f of x, and so this would be my f of, if I look at this, this is going to be my f of y, right? Over here, right? So let's see, so we're going to suppose that f of x is equal to f of y. Okay? So if f of x is equal to x of y, then that means that 3x plus 4 is going to equal 3y. Let's see, we're going to do a little math. So let's subtract 4. Subtract 4. And so we'll have 3x is going to equal 3y. Okay. And then, of course, I can now divide by 3. And we end up that x is going to equal And so we did write the inverse correctly, because when we do this, we got to come down to that statement, that x is equal to y, right? And so we did it right in our inverse, right?
Does y be in parentheses?
Yep, yes. Yep, yep, yep. Yes. Yep. Oh, yep. Okay? So therefore, is 1. So it is 1-to-1 function. So if it is 1-to-1, again you get into terms, okay? And so in terms of that, so 1-to-1, like we just talked about, the term you're going to see in terms of the book will be that, right? More terms, right? All right. So 1-to-1 you have a bijection, okay? Again, for every x we go in y, for every y we go in x, right? Right. So you got that term. The other term that you get is that they talk about is you get this term, which is onto. Okay. Another term. So let's say let f be a function that maps A to B. All right. So f is some function that takes an element of A and it matches it up with some element of B. Right? Okay. And so we can say that f is onto B, provided that for every B, which is an element of B, there is an A, which is an element of my set A, so that f of A is equal to B, right? So really what that means is that if I have a set A, I have a set B, every element of A better have a counterpart in B. There can't be anything left over. Basically, there cannot be any extra that you're not using, okay? So we want to have, so like if A had 5 elements and B had 10 elements, then we have a problem. Right? I got a whole bunch of things left over, not onto, okay? Right? So an example. We'll have let's set A. 1, 2, 3, 4, 5, 6. Set B. Every element of B has a counterpart in it. Okay? think in terms of up on the roof, you have the pigeon coop, and you have in terms of X number of homes in your coop, okay? So holes that the pigeons go into. So if you have 20 holes and you have 18 pigeons, you don't have a problem, right? But if you have 20 holes and you have 45 pigeons, you have a problem. Right? So you get the whole pigeonhole, right? And so you got let A and B, D by next sentence, okay? And but F, function F, which is going to take A and match it onto B, okay? Okay? So finite set, that means we can count the number of elements that are in there, right? Okay? Okay? So if the cardinality of A is greater than the cardinality of B, right? Then F is not 1-to-1. Okay? And then if the cardinality of A is less than the cardinality of B, then F is not unto. Okay. Right. If F is a bijection, then the cardinality of A is equal to the cardinality of B. Well, then in terms of function, we can combine them, and so you get what are called composition composite functions. Right? So if f of x is equal to 4x plus 3, and let's say that g of x is equal to 7x minus 5, and over here, if I ask you what is the f of 3, so what's going to be the f of 3? 15, right? This will be 15. And I ask you what is the g of 3? We get 60, right? Right. That's all that says. Given f of x, where we see the x, plug in the 3. Given g of x, everywhere you see the x, plug in the 3, and see what you get, right? All right. Now, what if I want to know what is the f of g of x, right? Well, really what this says now, it says start with the f of x. Everywhere you see the x, we want to plug in this. And so here we're going to have 4, and then we'll have times the 7x minus 5, and then the plus 3. And then we can do a little math. And so this is going to be 28x minus 20 plus 3. And so we get 28x minus 17. Right? And then we could do the same thing on this side. We could go and say, what is the G of f of x? And so now we would start with the G of x, and everywhere you see the x, we'll plug in G of x. So this is going to be 7 times the 4x plus 3 minus 5. And so this will give us 28x plus 21 minus 5. And so this will give us 28x plus 16. Okay. Right. So in terms of notation, f of g of x becomes this. So this becomes fog. And then g of f of x becomes golf. We got fog and we got golf. And so now if I ask, well, what is the fog of 3? What do we get?
F of G of x, right? That's what we called it.
Well, yep.
So you get 28x minus 17.
Right, and now I want to plug in the 3, and we get an answer of it.
Oh,
Now we're putting 3 in there.
Now, okay, now the light bulb went off. Okay.
67.
67, right? And then if I ask what is the golf of 3?
100.
And then we get 1, right? So composite functions. Right, right.
Yeah, I do.
Huh?
Just friendly banter back here.
Okay. Okay. And then you get to permutations. And so at A, be a set of A permutations. So now I'm going to say let A be the set. 1, 2, 3, 4, 5. And let F map A to A. Right? And so F is going to be the set. 4, 3, 1,
that for the point coordinates, it doesn't really matter, right? You're just grabbing random numbers from it.
Yeah, I'm just
Okay.
making, I'm just writing up one.
Yeah.
Okay, there's
Right.
several possibilities, right?
Yeah.
This is this is one possible group, right? Several number of groups, right? Right, yeah.
So, and let FA then.
So let F, alright, so F is gonna be my thing that maps A onto A.
Oh, A, okay, okay. I was just gonna ask.
So I'm gonna take an element of A and I'm gonna match it up with another element from A, right? That's what this is, that's what that's doing, right?
Okay.
And we're gonna say, this is what you get. Okay, and again, I can write out endless number of possibilities, right? Yeah, that's right. Well, 5 to the 5th power. Go right for a while. Yeah, right? Or not going to. All right. No permutation. So let's say I have let F be this side. 1, 2, 3, 4, which maps this to this side. 1. So we're going to take the elements 1, 2, 3, 4, we're going to map them into my other set of 1, 2, 3, 4. And in this case, we're going to define it, we're going to say how this pairs up, because again, there could be a variety of possibilities. And so I'm going to say that the f of 1 goes to 2, f of 2 goes to 4. Yeah, remember this is the way your x and your y, right? F of 3 goes to 3, and f of 4 goes to 1. Right? Right. So if I look at this, I have the numbers 1, 2, 3, 4, right? And we said that 1, so really these are my x numbers, and then down here I'm going to have my y numbers. So we said 1 goes to 2, right? And actually, let's do this color. So my 1 goes to 2. We said here 2 goes to 4. 3 goes to 3. And then 4 goes to 1. Right? And then I do this, throw a little curve there, with a curve there, and you get what is called cycle notation. Right? So 1 goes to 2, 2 goes to 4, 3 goes to 3, and 4 goes to 1. Right? Right. And then in terms of this notation, we can also then rewrite this in terms of a shorthand notation. And we just get the cycle stop. Right? Right. So in terms of this notation, if a number corresponds to itself, so the 3 went to 3, like we had, it doesn't show up in this, right? So what this tells you is that 1 goes to 2, 2 goes to 4, and then the 4 goes back to the 1, which is what we had up here, okay? So I can write it in just one line instead of couple, right? So given that I have this, right? So if I gave you this, then I said, okay. given that shorthand notation, I said write out the two-line notation, okay? So I got the shorthand. I want to know what does the two-line version of this look like, right? So we're going to assume that the largest number in my group is going to be the 7, okay? Right, so that's what, was just, we're going to assume we're going to stop at that point, okay? Right? And I want to know what would this look like in terms of a two-line notation. So I get my first, so this, and then the question is, okay, what goes down there in my bottom line? Given this example, right?
Four and 5 have their same number underneath them because they're given with a nutshell.
Right, they're not shown, so yeah. Yeah. But again, when we write the whole thing out, we gotta put the entire, we're gonna put the entire picture there. Right?
Doesn't really matter what other numbers you put as long as you put all of them.
Right? Well, again, we got, right? So we're gonna assume that we stop at this number, right? We're gonna assume we stop at this largest number, right? Because that was going, okay? All right. So we know we got the numbers from 1 to 7. Okay, so let's start here. The 1 goes to what?
Oh,
1 goes to
3, 7,
6.
oh,
yeah.
One goes to 6, right?
Oh.
I got that. You got that?
Yep.
All right. Okay, we got this. We got to start here. All right. So 1 goes to 6. Where does 6 go to? 3. Where does 3 go to? 1. All right. Okay. All right. 2 goes to what? 7. 7 goes to 2. All right. 4 goes to 4. And 5 goes to 5. Okay? All right? All right? We got that? So given this, can you then write that? Okay? Right? And so then again, the next possibility then would be, given this, can you write that? Right? So let's do this one. So given that, can you write the one-line version of that? What? Challenges. Right? But I know that you will rise to the challenge, right? Yeah. Oh, we got 2 down. going back to the drawing board. Alright, alright. Okay. Alright. Alright. So if I start here at the beginning with 1, right? Alright. And so we got 1 goes to 7. And then 7 goes to 8. 8 goes to 2. And 2 goes to 1. So that closes off our first loop. Right? Alright. Let's see. So let's go on to our next number being 3. Right? So 3 goes to 5. 5 goes to 6. And 6 goes to 3. So that closes off that one. Right? And let's see. That takes us now up to the number 4. And 4 goes to 9, and 9 goes to 4. Okay. And that closes that one. Okay? In this case, I don't have any number that's not being used, right? Everybody. Right? 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 We got that. All right? All right. Alright, one last thing then. No, this one's fine. Wait till you get to see this one. And all this. Alright. We'll do these. But pi, something to say pi, and pi is not going to be pi as in this cycle. 1, 2, 7, 9, 8, 5, 6, 3, and so the inverse of this, pi inverse, nothing really tricky, because all you gotta do to write the inverse here is take the numbers I had, change the order, okay? That's how we get the inverse, all right? And then, of course, we still have 4 out here. 4 is by itself, right? Well, we get our inverse, okay? So all I gotta do to write the inverse of a cycle is just flip the numbers, right? Right. 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 Now comes the fun one. Right? I go, let's see, just flip the numbers, right? Alright. So let's say we got this. So we got, let's say again I have pi, which is now going to be given by the cycle 1, 3, 5, 4, 6, 2, 7, 8, 9. And then I have sigma, which is going to be given by the cycles 1, 4, 7, 9, 2, 3, 5, 6, 8. And now I want to do the composition. Of the two permutations. And so now we're going to have We want to see what happens here, right? Okay, so now we want to see what we get when we bring this all together. All right. I'm going to start with, again, we're going to do our basically our flaws, right? We're going to start with this one, and we're going to see how it happens when we map it out to this one, right? All right. So we're going to work our way through and see how things work out, right? So we're going to start with our 1, right? So we start with the 1, right? So my 1 here, and this one, well, 1 over here, 1 goes to 4. So 1 goes to 4, okay? But then 4 over here goes to 6.
Oh, so jump back and forth.
So we're going to end up, we're jumping back and forth, right? So 1 went to 4, 4 went to 6. So there's my first number, 6, right? Right? Now, we're going to start with the 6, right? So we start with our 6, okay? And so 6 goes to 8, right? So 6 goes to 8, right? And then 8 goes to 9, right? And 8 goes to 9, right? That's my next number, okay? Well, 9 goes to what? 1. 9 goes to 1. And 1 goes to 3. Right? That's my next number. Right? Actually see that, be helpful. Right? There. Actually, let's just go over here, it'll be easier. Right? Right. So we got our 3. And so 3 goes to 2. 3 goes to 2. Right? And 2 goes to 7, right? That's my next number, right? And then we have the 7, right? And the 7 goes to 9. And the 9 goes to 2, right?
Oh, yeah.
All right?
Yeah, the other side, yeah.
Right? And then 2 goes to 3. And 3 goes to 6. No? 5.
Oh, right.
And then at that point, it ends up that we're done, because when I look at the next one, I would have 5, and 5 goes nowhere. Right? 5 is a dead end. Right? Yes.
So I pretty much get it, but I don't understand why 3 goes to 2. And like, I don't see where.
Because we go from the 3 to the first
Because
one
this
over to
one,
the 3 of the
remember
other one.
this one basically moved back and forth?
They didn't say so.
It'd be easier, let me go back to my, where we had it up here. Where we had it. So here's my 2, 7 thing. So 2 went to 7, and then 7 went to 2. They just go back and forth. Those two. Alright? so you end up going back and forth, okay, keeping track of where you are. And then you go until we get to the dead end. In this case, the dead end is 5. Because 5 at that point goes nowhere. That's all. 5 is just here. It does not go to any other number but itself. Okay?
Wouldn't you know that that would be your dead end since it's by itself in parentheses? You start with
Yeah.
five.
Yeah, and then depending on how this all worked out, depending on the other number combination, would be how quickly do we get to that dead end, right? Depending on the cycle. Okay. Okay. All right. Okay. Any other question on that? No. All right. All right. Let's call that. Let's see. Yep. All right.